Let's start off with some tips on working friction problems. These are going to be some general rules of thumb here for doing friction problems both on horizontal surfaces and on inclined planes. Okay, so let's start off up here. I begin by giving you the equations for maximum static friction and kinetic friction. In both cases, it is the coefficient of friction times the normal force. So with friction problems, the first step you'll want to do is, of course, draw your force diagram. Draw the diagram of all the forces acting on your object. Then let the x-axis be in the direction of movement or possible movement. And the reason for that is because if you look at step number 3 here, in the direction of no motion, that will be the y-axis. If we choose the x-axis to be motion, then the y-axis will have no motion, and the sum of the forces in the y will be equal to 0. After you draw your force diagram, second step, resolve any forces that aren't on the x and y axes into their x and y components. So after step 2 is completed, you should have forces that are only in the x direction and only in the y direction. Then, like I said already, the sum of the forces in the y will be equal to 0. The normal force will be one of those forces in the y direction. So you'll want to isolate the normal force, solve for the normal force, because that's what we're going to use in our equation in the x direction for friction up here. The force of friction in the x direction will be the coefficient times the value of the normal force, which we'll get in step 3. Then finally, in the direction of motion, now the sum of the forces in the x direction will be equal to mass times acceleration in the x, and we can use the equations that we've got for, in step 3 and up here to help solve for the value of the frictional forces, if that's what is being asked, or maybe the acceleration, whatever's being asked for. In step 4, that's where we'll solve for that. The first example we'll look at is a box at rest on an inclined plane. So step 1, draw all the forces that are acting on my object, on the box. So the weight of the box, the normal force is acting on the box, and the static frictional force is what's preventing the box from slipping or sliding down the incline. Then step 2, resolve any forces not on the x or y axis into its x and y components. And that's what I've done here with the weight. The static frictional force is already on the x-axis. The normal force is already on the y-axis. But the weight needs to be resolved into its y component and its x component. Then, step 3, in the direction of no motion, let the sum of the forces in the y be equal to 0. And that's what I have here. And because it's at rest, I know also that the sum of the forces in the x is equal to 0. Okay, so this is just telling me that because the acceleration in the x and the y is both equal to 0, then I know the sum of the forces in both the x and the y is equal to 0. This is a situation called static equilibrium. Now let's do a little further analysis with step 4. The sum of the forces in the x direction equals mass times acceleration in the x direction. So if this angle was 0, in other words, if it was on a horizontal surface, let's just look at this before we incline it. The sum of the forces in the y is equal to 0. The normal force is in the positive y direction, so it has a positive sign. The weight is in the negative y direction, so it has a negative sign. There's my sum of the forces equal to 0. Rearranging, I see that the weight and the normal force are equal to each other. For a horizontal surface, it's important to note that, for a horizontal surface, when there are no other forces in the y direction, this will be true, that the normal force is equal to the weight. And then in the x direction, there is no x component of weight when theta is 0, so there is no static frictional force. Remember, friction opposes motion or trying to move something, but if the surface is horizontal, it's not trying to move. So there is no static friction. But now let's raise this plane so it's inclined, and we'll say that the angle theta is the angle of inclination. So as that increases, as the plane becomes inclined, now the sum of my forces in the y still equals 0, but now instead of the weight, it's the y component of the weight. And I see that now the normal force is equal to the y component of the weight, not all of the weight, just the y component. And in the x direction, because the box is not sliding yet, the sum of the forces in the x is still 0, and now I have an x component of weight that is I've chosen that to be the positive direction down the ramp, and the frictional force is up the ramp, so I've chosen that to be the negative direction. So I see that the frictional force is equal to the x component of the weight. And as theta increases, the normal force is going to become smaller because the cosine of an angle, the angle gets bigger, becomes smaller. And the frictional force will become larger as theta increases because as an angle increases, the sine of that angle increases. Let's look at the situation again, but now the difference is the box is sliding down the inclined plane. It's not sitting still, but it's moving. You'll notice that our force diagram of the forces acting on the box, it looks almost the same, almost identical to the one as when it was at rest. The only difference now, though, is that the frictional force is Fk. It is a kinetic frictional force, not a static frictional force. Everything else, though, is the same. So if it's not accelerating in the y direction, remember we chose our x direction to be the direction of motion for this very reason. So now the sum of the forces in the y is equal to 0, and just as in the previous example with the static box, the normal force is equal to the y component of the weight. And in the x direction, we have a net force. The x component of weight is going to be greater than the kinetic frictional force. So this sum of forces here will be some non-zero number. So if I have some value for the sum of forces, that means I will have an acceleration. And so I set it equal to mass times acceleration, where acceleration is not 0 this time. The x component of the weight is equal to w sine theta. We can see that from this diagram. The frictional force, using our equation for friction, is mu times the normal force. So I've made those substitutions. Then, in addition, I made one more substitution in the next step here. The normal force I've substituted for with its equivalent value of w cosine theta. And then I've solved this equation for the acceleration in the x direction. So I see that the acceleration will be equal to the weight times quantity sine theta minus mu k times cosine theta, all divided by m. And you could take this one step further. If you wanted to replace w with mg, you would notice that that m and this m would cross off, and the acceleration would be equal to g times sine theta minus mu k cosine theta. Now, I don't recommend you memorize this equation. I would say don't memorize it. What's important is to get good at this process of looking at the sum of the forces in the y, setting it equal to 0, solving for the normal force, and then using that value for normal force down here in your x equations when you are trying to find out what the friction is, mu times the normal force. You can use your result from the y direction to plug in here for Fn, and then solve for the acceleration in the x. The reason why I don't recommend you memorize this equation is because sometimes subtle things change or might be different than what's in this diagram, and so the analysis would yield a little bit of a different answer. But the process is always going to be the same. Let's take a look at an example. We have an inclined plane with a box filled with delicious Twinkies weighing 10 newtons, and the angle of the incline is 20 degrees, and the coefficient of static friction between the box and the ramp is 0.25 for static friction and 0.15 for kinetic friction. So let's answer this question. What is the least magnitude of the force labeled F parallel to the plane that will prevent the box from slipping down the plane? So we start off by drawing our force diagram. All right, so step one, draw a force diagram acting on the box, of all the forces acting on the box. So the weight, of course, the normal force, which is perpendicular to the surface, and the force that's holding the box from slipping down the ramp. Okay, so if we're trying to find the least amount of force that prevents it from slipping down the ramp, I haven't included friction in the diagram yet because you have to figure out which way the friction is acting. If we're trying to prevent the box from sliding down the ramp, that means the friction is up the ramp. So when I add my frictional force, there it is. Okay, it's up the ramp because it says that the box wants to slide down the ramp. Okay, step two, resolve any forces that aren't on the x or y axis into its components. And we see that W, the weight, is the only force that is not on the x or y axis already, so we resolve it into its x and y components. There's my Wx, and here's my Wy. Okay? Now, step three, in the direction of no motion, the y-axis, sum the forces to 0. The sum of the forces in the y is equal to 0, so I have Fn minus Wy equals 0. So that tells me that the normal force is equal to the y component of the weight. Okay, and a little more analysis shows that if this is theta here, this is theta here, and the y component of the weight is the adjacent side to that angle, so that's going to be W cosine theta. So the normal force is the y component of the weight, which is W cosine theta, and we have the information to plug in to get a numerical answer. And we see that the normal force, 10 cosine 20, that's equal to 9.4 newtons. Okay, so step two allowed me to solve for the normal force. Step three, I'm going to sum the forces now in the x direction. It still equals 0 in the x direction because the box is at rest. So I'm going to look at all my forces in the x direction, and I've chosen the direction of possible movement to be the positive x direction, so that's down the ramp. So the x component of the weight is in the positive direction, and then the static frictional force and the holding force of the string is there both in the negative direction. And so now I can move this. This is what I'm trying to solve for, the holding force of the string. So I'm going to move that F to the other side, and I see that that is going to be Wx minus Fs. Okay? Wx, looking at in my diagram, the x component is opposite of theta, so that's the sine function. And the frictional force we know is equal to mu s times the normal force. Okay, so now I can go ahead and plug in numbers for all these things. 10 sine 20 degrees minus 0.25, and the normal force was over here, 9.4 newtons. So 10 sine 20, that is 3.42, minus this number is 2.35. So I get my answer then, 1.07 newtons is the minimum force needed to hold the block in place and prevent it from sliding down the ramp. So we figured out what is the minimum force to hold it in place. Now let's find out what is the minimum force needed to get the box to slide up the ramp. Okay, so step one, draw the force diagram. We still have the weight. We still have the normal force. We still have a force directed up the ramp. Which way is the friction? Well, if I'm trying to pull the box up the ramp, that means the frictional force is going to be opposite of that, or down the ramp. Since we chose the positive direction to be this way on the last part, let's do it that way again. Okay, so in the y direction, nothing has changed. The sum of the forces in the y is still equal to 0, and Fn minus mg equals 0, and, oops, not mg. In the y direction, it's mg cosine theta. It's the y component of the weight. So let's call it Wy equals 0. So the normal force is equal to Wy, which is W cosine theta, which is still the same value as before, 9.4 newtons. So in the x direction, something is different. Because now we're trying to pull the box up the ramp, the frictional force is down the ramp. So we're going to sum our forces. F is in the positive direction, F is in the minus direction, and the weight, the x component of the weight, is also in the positive direction. And that equals 0. Why does it equal to 0? We're just trying to get it to start to move. So that means we're looking for the maximum static frictional force. Okay, the maximum static frictional force, that's like the tipping point. That's when it begins to move. So if we analyze that point where it is still not moving but just about to move, that's still an acceleration of 0. So the sum of the forces still equals to 0, and this is Fs max. Okay, the maximum static frictional force. Okay, so Wx is still W sine theta. The friction is mu s times the normal force minus F equals 0. This is what we're trying to solve for. So 10 sine 20 degrees plus 0.25 times the normal force, 9.4, equals F. And so this turns out to be now 3.42 plus 2.35 gives me an answer of 5.77. So that's the amount of force I need to just begin to pull it up the ramp. Lastly, let's calculate what is the value of F required to move the box up the plane at constant velocity. Okay, step one, draw the force diagram. These forces are still the same. The weight is still there. The normal force is there. The pulling force that we're pulling with is still there. But where's the friction? Well, we're trying to pull the box up the ramp, so the friction is down the ramp. And remember now, it's sliding up the ramp at constant velocity. So that means we're going to use kinetic friction because it is sliding on the ramp. Okay, in the y direction, nothing has changed. So I'm still going to come up with the normal force is equal to 9.4 newtons. Okay, that's that we found in the previous two examples. I'm not going to redo it there. Okay, now in the x direction, sum of the forces is mass times acceleration in the x, but it says it's moving up the ramp at constant velocity. So there's no acceleration yet again. And in the positive direction, I have Fk, the x component of weight, and the pulling force F is up the ramp. Fk now is mu k.
times the normal force, plus the x component of weight is W cosine theta, and move that F to the other side. So mu K now is 0.15, the normal force 9.4, the weight 10 newtons, and the cosine of the angle 20 degrees is going to be my pulling force up the ramp, and so that is 3.42 plus 1.41 equals 4.83 newtons. That is the force needed to pull the block up the ramp at constant velocity. Notice that this force, 4.83, is less than 5.77. This was the force needed to just get it to move, to break the static frictional force. And then once it began to move, it requires a lesser force, 4.83 newtons, because now we're dealing with kinetic frictional force, which we know is less than maximum static frictional force.